Okay, we're going to wrap up with a section on rational functions here. So finish the section on functions with rational functions. Okay, a rational function is just a function where you have a numerator that's a polynomial and a denominator that's a polynomial. Actually, all polynomials technically are rational functions because you could say they're over 1. But rational functions, when we say rational functions, we generally get more specific functions that look like 1 over x or this function or maybe something like this. Okay, so let's talk about the domain. I won't spend much time on this because we've already talked about domain. But this function, x cannot be 0, so therefore in interval notation you'd say the domain is negative infinity, 2 but not including 0, union 0 to infinity. Now, if this function, actually the denominator will factor. So to determine the domain of this function, you say, well, what would make x cubed minus 8 equal 0? Well, down here, you'll notice that I've factored that using the difference of cubes, factoring. So you get x minus 2 times x squared plus 2x plus 4. Well, this trinomial will not factor over the reals, so there's no real solutions to that if we set that equal to 0. But x minus 2, what makes it equal 0 is just x equal 2. So x cannot equal 2 here because that would give us 0 as the denominator. In interval notation, negative infinity to 2 and union 2 to infinity. Notice that we don't include 2 in those. Okay, now I won't factor this because you actually know what this factors into. It's difference of squares, and it factors into x plus 5, x minus 5. So if we say, well, what makes the numerator 0 here, the denominator 0 here, then it would be either plus 5 or minus 5. So x cannot be plus or minus 5, therefore the domain here would be negative infinity to negative 5, union negative 5 to 5, union 5 to infinity. That just means all real numbers except minus 5 and plus 5. So now let's talk about the intercepts of these three functions. This function, you would normally let x be 0 and see what y equals to get the y-intercept, but x cannot be 0 in this one, so there's no y-intercept. And then you would set the function equal to 0 and solve for x to get the x-intercepts, but there's no way that 1 over x can equal 0, so you don't have any intercepts for this one. This one doesn't cross the x or y axis. Now for this one, to find the y-intercept, you let x be 0. Well, if you do that, these two terms would disappear, and you would just get 1 over negative 8, which is just negative 1/8. So the y-intercept there is 0, negative 1/8. Now to get the x-intercepts, you would simply set this equal to 0. Well, the only way that a fraction can be 0 is if the numerator is 0 and the denominator is not 0. So what makes the numerator 0 would be right here, if x squared minus 2x plus 1 equals 0. Well, that factors into x minus 1 quantity squared, and the only way that can be 0 is if x equals 1. So the x-intercept here is right here, 1, 0. Now the third one, if you let x be 0 here, then this term and this term disappear, and you get minus 3 over minus 25, which is 3/25. So the y-intercept is 0, the point 0, and 3/25. Now if you want the x-intercepts, what you do is, again, you set this equal to 0, and again the only way it can equal 0 is if the numerator is 0. So if you set the numerator equal to 0 and then solve for that, you get x equals 3/2. So the x-intercept here is 3/2, 0. So, excuse me, 3/2, 0. And in order to see that, you can graph each of these and see where the graphs cross the x and y axis, and then from that you'll see that they actually cross at the points that I'm giving you here. Okay, next I want to talk about vertical asymptotes. Vertical asymptotes are just kind of imaginary lines that can be used to help graph rational functions. A vertical asymptote occurs when the function increases or decreases without bound as x approaches a real number. So if you take a look at this function, you'll see I've got this dashed vertical line drawn here, looks like that's at x equal 2. Well, notice that as the function approaches 2 from the left, notice how the function decreases without bound, and as the function approaches 2 from the right, the function increases without bound. In the second one, you'll see I've got this horizontal dashed line drawn. Well, that's y equal 2. So notice that a horizontal asymptote can occur as x approaches plus or minus infinity, and the function approaches a horizontal line. Well, this function, notice as x gets large, this function gets closer and closer to the horizontal line, and also as x gets very, very small, it approaches that same horizontal line. So that's a horizontal asymptote. And then a slant asymptote, also known as an oblique asymptote, can occur when x approaches plus or minus infinity and the function approaches a non-horizontal line. So if you look at this graph, you'll notice that as x gets large, this function gets actually closer and closer and closer to that slanted line, and then as x gets very small, the function gets closer and closer and closer to that slanted line. So that's you a visual picture of what these three types of asymptotes look like. And next I want to show you how you can find these particular asymptotes from a given function. Okay, so first let's talk about vertical asymptotes. Vertical asymptotes are generally pretty easy to find. What you do is you find the numbers that make the denominator 0, and as long as they don't also make the numerator 0, they're vertical asymptotes. So here x makes the denominator, or 0 makes the denominator 0. So here we would get a vertical asymptote at x equals 0. The next one, notice I went ahead and wrote it in factored form. You can see here that 2 makes the denominator 0 and it doesn't make the numerator 0. So here we have a vertical asymptote at x equal 2. And then here I factored the bottom into x minus 5x plus 5, and you can see that 5 or negative 5 makes the denominator 0. So here we get two vertical asymptotes, one at negative 5 and one at positive 5. And that's how you identify vertical asymptote. I wanted to show you one more function here. Notice this function, x minus 3 times x squared over x minus 3 times x plus 1. Now, in most cases, you can cancel x minus 3 over x minus 3 because that equals 1. But the only time you couldn't cancel x minus 3 over x minus 3 is if x equaled 3. Because if in that case, then you would have 0 over 0, which is actually undefined. So as long as x does not equal 3, we could write this as x squared over x plus 1, which would have a vertical asymptote here of negative 1. But what's happening at 3? Well, actually, if you graph this and you tried to find what's happening at x equal 3, you would actually find that there's a hole there. And the hole would actually be at x equal 3, and it would be at whatever this equals at 3, which I think would be like 9/4. But that's what happens. So that's why we want to make sure when I say if you want to find a vertical asymptote, you find out what values make the denominator 0 but don't make the numerator 0. Because if a value makes both the denominator and the numerator 0, you actually get a hole at that number and not a vertical asymptote. Now let's talk about horizontal asymptotes. There's three cases you can consider here. The first case is if the numerator is less than the degree of the denominator, then the horizontal asymptote is just the line y equals 0, which is the x-axis. So that's what's happening here. Here the numerator has degree 1 and the denominator has degree 2. Well, since the numerator has degree smaller than the degree of the denominator, we get a horizontal asymptote at y equals 0. The second case says if the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is the ratio of the lead coefficients. Well, here in the top we have a degree of 2, in the bottom we have a degree of 2. So look at the ratio. The lead coefficient in the top is 2, the lead coefficient in the bottom is 3. So the horizontal asymptote in this case would simply be the line y equal 2/3. And then if the degree of the numerator is greater than the degree of the denominator, like here 3 is greater than 2, then we actually have no horizontal asymptotes because this graph as x goes to plus or minus infinity actually either increases or decreases without bound. So that's how you identify horizontal asymptotes or the lack of horizontal asymptotes. Now the last thing I want to talk about is slant asymptotes. Slant asymptotes occur when the degree of the numerator is just 1 unit greater than the degree of the denominator. So for instance, this graph here, the degree of the numerator is 3, the degree of the denominator is 2. Since 3 is 1 greater than 2, this would have a slant asymptote. Same thing here. The degree of the denominator is 1, the degree of the numerator is 2. This would have a slant asymptote. Now, let's go ahead and look at the graphs of some of these graphs that we've been talking about. So this function here we found had vertical asymptotes at -5 and 5. And notice that over here, this is the vertical line x equal -5. This is the vertical line x equal 5. And notice how the graph either increases or decreases without bound as it gets close to these lines. We also found that we had a horizontal asymptote of the x-axis, and notice how the graph gets closer and closer to the x-axis as it increases, as x gets very large or very small. And so y equals 0 is the x-axis. That's your horizontal asymptote. And then we found the intercepts were 0, 3/25, so there's the y-intercept, and the x-intercept was 3/2, 0, and so there's the x-intercept. Okay, I want to do number 3 next. This one we can see has a horizontal asymptote of y equal 2/3, and if you look at this horizontal line here, notice that as x goes to infinity, the graph tends to get closer and closer to this line, and as x goes to negative infinity, the graph gets closer and closer to the same line. If you get the x-intercepts here, let x be 0, you're actually going to get -1/2. And so that's the y-intercept. So the y-intercept right here is the point 0, -1/2. You can see it crosses the y-axis here. Now, to get the x-intercepts, you have to actually set this numerator equal to 0, and I'll let you do that. But if you do that, you'll get 2x squared equals 1, and x squared equals 1/2. So x actually is going to be plus or minus the square root of 1/2. And so right here you can see the graph. Right here the graph crosses the x-axis, and that's where x is negative square root of 1/2, and over here it crosses the x-axis, and that's where x is positive square root of 1/2. And so that's how we use that information to graph that particular function. Okay, now this one, the degree of the numerator is 1 greater than the degree of the denominator, so this is how we find the slant asymptote in that case. What you do is you do long division. You divide x plus 2 into 3x squared minus 1. And when you do that, you'll get x times 3x. You'll get 3x for the quotient, and then you multiply back, get 3x squared plus 6x, and then subtract, and then you get minus 6x minus 1, and then so you say, what times x gives me minus 6? It's going to be minus 6. So then you multiply that, and then when you subtract this, you'll get a remainder of 11. Well, we don't really worry about the remainder, because the remainder goes to 0 as x gets very, very large or very, very small. We just worry about the quotient portion. The quotient portion is the slant asymptote. So the slant asymptote here is y equal 3x minus 6. And this dotted line here that I drew is the line y equal 3x minus 6. Now I'll leave you to find the intercepts. The intercepts are 0, -1/2, and plus or minus square root of 1/3, 0. It's kind of hard to see here, but if you look real close, you can see on each side of 0, it crosses the x-axis, and that would be your x-intercepts plus or minus the square root of 1/3. And then right here it goes just slightly below the x-axis and crosses the y-intercept, and that's where you get the point 0, -1/2. So to see it better, you might have to graph it again and blow it up to see those intercepts. But that's basically the graph. So that's how you graph rational functions. And finally, we get finished with the section on functions.